let me remind you which were the two problems. The two problems were, if the weak interaction is described by the Yang-Mills theory, that was the theory which of the local symmetry, then the weak interaction cannot be a short range because the particles seem to be were massless particles. But what we saw now is because of the Higgs field, the same particles which are massless but when in presence of a Higgs field behaves like a massive particle. So that problem is solved. Now we have one more problem, right? Because to describe a mirror world, I had to assume that electron and quarks and every particle that experiences weak interaction is massless particle. But we know in the real world they are not massless particle. Let's see how Higgs field solves that problem too. Well, it turns out when we say some particle has a mass, like a particle, particularly a particle like electron or a quark has a mass, what it really means is that, remember I said that electron can come in two varieties, that they could be spinning in the along the direction of motion or spinning opposite to the direction of motion. But if they have a mass, then a particle which is in a left-handed particle that is spinning opposite to the direction motion can get converted into a particle which is spinning along the direction of the motion. So what mass does is that it sort of oscillates, it switches a left-handed electron into a right-handed electron, a right-handed electron into a left-handed electron, and that is what the mass does. So I cannot just convert a left-handed electron into a right-handed electron because the charge has to be conserved, the weak charge has to be conserved. So let's see how this problem is solved by the Higgs. Remember, the Higgs field carries an indefinite amount of charge. So there's a massless left-handed electron comes, but it is moving in the Higgs field. So what happens? It interacts with the Higgs field, it dumps that charge to the Higgs field. Higgs field can absorb that charge, and by dumping that charge, it becomes a right-handed electron. Now right-handed electron moves for a while, again interacts with the Higgs field, it takes a charge from the Higgs field and becomes a left-handed electron. So in the end, what we see is that the effect of the Higgs field is that the left-handed electron is becoming right-handed, right-handed is becoming left-handed, but that's what the mass does to the particle. So the effective presence of a Higgs field converts a massless electron or a massless quark precisely into a massive quark. So even though the theory at a fundamental level is a theory of a massless particle, but these massless particles are propagating always they are propagating in the presence of this Higgs field. We start with a theory in which the quarks and electrons did not have any mass, but when the quarks and electrons move in the presence of a Higgs field, they behave just like a massive particle. Now let me come back to the so-called God particle. Now Higgs particle has been labeled by a lot of people as a God particle, but it's interesting to remember the origin of this phrase. Leon Lenderman, who is an American physicist, was responsible for discovering one of the elementary particles, the top quark, and then wanted to discover Higgs. Everyone was trying to discover the Higgs particle. But he tried and he couldn't find it, and a lot of people tried to discover this Higgs particle and they couldn't find it, and in frustration he said that goddamn particle. So that goddamn particle became a God particle, and that was just a sort of a media hype. So what he wanted to convey was that it was extremely difficult to detect this particle. But let's try and understand where does this particle comes from. Well, this particle comes from the fact that, as we've just now discussed, that everywhere in the universe there is a Higgs field. So imagine this, just as an analogy, imagine this Higgs field like it's like a air in this room. So everywhere in this room there is a density of air which is same everywhere. But when I speak, I create waves. So the density is disturbed. And that disturbance and density are the sound waves which goes to your ear, and that's how you can hear me. Now, by analogy, I have this Higgs field which is filled everywhere in the universe. If I could make waves, if I could sort of splash into that pond of Higgs field, I would create these waves. And these waves, according to quantum mechanics, would be also equivalent to some particle, and these are precisely the Higgs particle. Now, why is it so difficult to discover them? Well, it is the Higgs field, it is very difficult to sort of give energy to the Higgs field. It took the largest experiment that humankind has done to discover the Higgs particle. And the way they did was at the Large Hadron Collider at CERN in Geneva, they took two beams of protons, accelerated them to a very high speed, almost to the speed of light, and made them collide. When they collide, there's a process by which a Higgs particle was created. So what they did is, essentially in some sense, they created this wave in this pond of Higgs field. And this wave then moved through this vacuum, and after a while this wave decayed into two particles, and those two particles turned out to be two gamma rays, and these two gamma rays were detected by the experimentalist, and that was the signature of the Higgs field. The discovery of Higgs boson, and before that the discovery of many other particles like W plus, W minus, Z naught, has given us a huge confidence in our description of nature using the idea of standard model or using this idea of local symmetries. But our understanding is hugely incomplete because we do not understand why different particles have their masses. I told you the way the Higgs field gives a mass to an electron. But it could give a mass to electron which could be 1 ton, or it could give a mass to electron which is 1,000th of a ton, 1 billionth of a ton. How much mass the Higgs field gives to the electron is a number which our theories cannot determine. It is a number which I have to put it by hand in my equation. So our understanding is very incomplete right now. We do not understand why the different particles have the masses they have. In fact, the range of masses that elementary particles have takes all over the place. So we have complete lack of understanding there. We do not even understand why Higgs particle has this particular value of mass. And that is related to the nature of the energy the Higgs field has, that how much energy it will have for different values of the Higgs field. We know from the motion of the galaxies, motion of the stars in our own galaxy, we know it from the way the light bends around the stars, etc., that the universe is made up of matter which is not quark, which is not electron, it is something which we do not know. So there is a stuff out there which is not described by standard model. So the real adventure in a sense now starts. Right now the Large Hadron Collider is going through an upgrade so that the beam of the protons energy will be increased, and it will start again the experiments in 2015, and we are hoping that those experiments will give us some clue to some new particles which we have not dreamt of, which are not there in our theory, but which may tell us something about the existence of dark matter. Maybe they will give us a clue as to why the different particles have that masses that they have. And so the journey is unfinished. And okay, thanks very much.